Right, so now that we've already known what polar coordinates are, so we already covered what polar coordinates are. Let's remember that polar coordinates in circular motion, since radius is constant, since the radius is constant, we only have to take into consideration our angle with respect to the origin. So this is the thing, this is the variable. So as you can see, this would imply one dimension, this would imply another dimension, right? Uh, so along a circular path, okay, uh, if my radius remains constant, the only variable that is changing is my angle with respect to my origin, correct? Okay, so this is theta 1, this is theta 2. Okay, so as you can see, circular motion is one-dimensional motion. So circular motion is one-dimensional. Okay, if we're moving along a uniform circle, okay, because that means that our variable r is not changing. Therefore, the only variable that is changing is theta. Therefore, we only have one dimension motion. Okay, so let's just step back a little bit and remember what normal straight line motion was. So straight line motion, okay, we started with kinematics. Okay, kinematics have to do with three variables, which are position, velocity, and acceleration. Okay, so we call this S, V, and A. Okay, this is straight line motion. Okay, and these are the variables: position, velocity, and acceleration. So given a straight path, so let's call this our origin. Okay, let's put it origin. Let me put this away. Okay, so given our origin, this would be x0, this would be final x. Therefore, my position, my change in position would be, well, position is given by x, right? The position of my particle along this straight line is given by my variable x, okay? My velocity is given by my change in position over a change in time, right? So how did I move from this position to this position? So this would be x minus x0 divided by a certain interval of time. Again, remember, we're moving over one dimension, right? So my velocity would be my change in position. So how fast did it take, how long did it take for me to get from here to here, change in position, over a certain interval of time? And finally, acceleration is my change in velocity over time, okay? Because maybe my velocity is changing at, I have one velocity at 1 second and then another velocity at another point in time. Therefore, if there's a change in velocity, there is definitely an acceleration. So it's called this v minus initial velocity over a certain interval of time, okay? But now let's make a jump into, let's put this here like that. Put this away. Let's make a jump into circular motion. Okay, you guys, you shouldn't be scared whatsoever with this because this is still one dimension, right? As I explained here, right here, since our distance, this r variable, is not changing, the only thing that is changing is theta, right? So for example, in horizontal movement, my y variable remained constant, and what was changing was my variable of x, okay? In this case, it's the same. R remains constant, and what is, in this type of motion, what is my position? So let's call this S again. I'll put this away, sorry. So my position in this type of motion is not described by S or X, it's described by something we call theta. Okay, so my position within this circle, okay, so it could be at theta 1, at theta 2, at theta 3, at, whoops, put that line better. It could be at theta 4, whatever. Okay, so my position within this circle can be described only with my variable theta. My velocity remains just as this one, as a change in position over a change in time. Okay, so right now what this topic is called, what I'm talking about is angular quantities. Okay, angular quantities, they're called angular quantities because they relate to the angle. Okay, so in this point here, our velocity is my change in angle, so change in position over a change in time. This is called angular velocity. Angular velocity, angular position. So angular velocity is described by this letter omega. And if we have angular velocity, then we must have something called angular acceleration. And this is my change in angular velocity over my change in time. Okay, and this vector is called alpha. Okay, so now let's look at how these things look even better. So, but I want you guys to know, what I want you guys to know and figure out is that there's a correlation between these two types of motions, right? Okay, so in a straight line motion, we have position. In a circular motion, we have angular position. Okay, in a straight line motion, we have velocity. Here we have angular velocity. In straight line motion, we have acceleration, and here we have angular acceleration. Okay, so let's look at a new layer. So let me draw a circle. See how it goes. Okay, 1, 2, 3, go. Okay. So picture that we have a particle here and a particle here at this point. Okay. Okay, so let's mark our origin here. And let's say that this particle, remember with polar coordinates, oh, you know what? I'll do it with another color. So this particle here, so a particle at t1, so at time 1, this is the position of my particle. It forms this angle with respect to the horizontal, so theta 1 and r. Okay? Now, at time 2, so particle at time 2 is forming, well, it has this distance from my origin, which should be the same as this one. Okay, it's not because of my drawing, but if it was like a nice circle, it would be the same distance. And the position is this angle right here, so theta 2. So remember, okay, remember that, so this is position. Position depends on time, okay? If we want to have the velocity, so my change in position over my change in time, okay, this angle would be my change in position. Okay, so this angle is theta 2 final position minus initial position. So I moved this angle right here. I moved this angle at a given point in time. So this is the concept of angular velocity, okay? How much angle I am moving at what given time. So this is why it's called angular. Okay, because what I'm measuring is angles, okay? How much this how much I moved, how much this angle is within a given within a certain interval of time. Angles are measured in radians. Okay? Therefore, my angular velocity has units radians per second. Okay? Radians per second. How many radians? So how many? Yeah, radians is a measure for degree. And remember to change from degrees to radians. I know that 180 degrees are pi radians. Therefore, whatever value of degrees, so x times pi divided by 180 would give me my radians. Okay? And radians have to do with the radius. Okay, so 1 radian would be uh, 1 radius here. Okay, if you don't know what radians are, I can make a video of it. But okay, so our angular velocity is described by radians per second. How many radians, how many degrees of how many angle units I moved within a certain interval of time. And if I also have a change in angular velocity over time, that implies alpha, okay? And that is how many radians per second I changed per second. So this is equal to radians per second squared. Okay, so these are the angular quantities. Okay, and well, just to make things a little bit more confusing, but you don't have to worry about this right now. All of these are vector quantities as well. Okay, so both omega and alpha, the vectors, the direction that these vectors go, are perpendicular to these vectors, but in the third plane. So imagine that this is a circle in this plane right here. My omega vector would be perpendicular like this. Okay? If it goes up, that implies movement in this direction. If it goes down, it implies movement in this direction. Okay? Alpha is the same thing. But don't worry if you don't understand this right now. I just want you to understand what angular velocity is and what angular acceleration is and what angular position is. Okay? So thank you for watching the video. I think we can start looking at accelerated motion.